So welcome everybody in this week seminar. We have a pleasure to host Shishir Khandelwal from Lund University, who will be talking about his recent results with Armin Tavakoli on projective simulation of quantum instruments. So it's great to have you, Shishir. The screen is yours. Go ahead.
Right. Thanks, Miha, and thanks for the invitation. I'll be talking about some recent results on the projective simulation of quantum instruments. So the plan is to first introduce some preliminaries, which most of you would already be familiar with. And then I'll motivate the problem that we try to tackle in the work, presenting two main theorems. And then I'll move to three applications that we focus on in the work applied to qubit instruments. And lastly, I'll give some insights on high-dimensional instruments. So let me first briefly talk about projective and generalized measurements. So in ordinary courses on quantum mechanics, we deal with projective measurements, and specifically a projection-valued measure, PVM, is a set of projection operations, PI, such that a few conditions are satisfied. First of all, the operators are projectors. Secondly, they're orthogonal, and thirdly, they sum up to 1, which is the normalization condition for a complete set of projectors. And we also know that the probabilities are given by the Born rule, which states that the probability is just the trace of the operator times the state of the system. A simple example is a basis measurement for a qubit, in which the measurement operators take this simple form. But this is only part of the story, and one can think of more generalized measurements which don't satisfy some of these conditions. For example, a POVM is a set of positive semi-definite operators such that this normalization condition is satisfied. You will notice that I've dropped two of these conditions of orthogonality and projectivity. Because we've removed some of these restrictions, we can now describe some more general measurements. For example, this basis measurement that I showed here, now with white noise, and you can convince yourself this is not projective and this is non-orthogonal. So it's natural to ask whether POVMs can be simulated using POVMs. And for this, there is a famous theorem, which is Naimark's dilation theorem. Given a POVM on a Hilbert space, there exists a PVM, and there's a typo here, on a larger space and an isometry such that we can obtain the POVM elements by the application of the isometry on the projectors. And the probability and the measurement statistics can be reproduced by using the projector that we obtained through this theorem. So what basically it says is that all POVMs can be simulated by PVMs on an extended space along with an isometry. So if we have access to a larger Hilbert space and control over it, we can perform any POVM measurement as a PVM. But it's also natural to ask, can some POVMs be simulated by PVMs without ancillary degrees to freedom? And the answer is yes. It was actually introduced by Mihao in this work from 2017, where they found that PVMs and classical randomness can allow the simulation of certain POVMs. But it's important to note here that the focus is on measurement outcome or the statistics only and not on the post-measurement state. To talk about the post-measurement state in addition, one has to talk about a slightly more complicated object called a quantum instrument. So first of all, in a measurement, we're just sending a state to a measurement box and obtaining a classical outcome A. And these operators are, of course, form a POVM. And the probabilities are given by the Born rule. And these operators satisfy this normalization, which is that they sum up to the identity. And on the other hand, for an instrument, we're sending a state to an instrument obtaining a classical outcome and also a post-measurement state. So an instrument is not just a measurement operation, it's a set of subnormalized quantum channels such that we obtain a classical measurement outcome and a post-measurement state. So here, again, the probabilities are just the trace of the subnormalized post-measurement quantum states, and the normalization condition translates to this. And as a side note, one can also obtain the POVM elements from the quantum instrument by writing the quantum instrument as Krauss operators and then expressing the POVM elements this way. Another thing that will come in handy to understand the results was channel state duality. So let's consider that we have this instrument with the subnormalized channels IA. What channel state duality tells us that each channel can be associated to a bipartite operator which is positive semi-definite, such that this operator is defined as the local operation of this channel on a maximally entangled state, and here's the maximally entangled state in d dimensions. The complete positivity of each of these subnormalized channels translates to the positive semi-definiteness of the Choi operator eta A. And the normalization condition that the whole instrument gives you a normalized state corresponds to the fact that locally this Choi operator is maximally mixed. And what's nice about this definition is that one can directly obtain both the channel and the POVM elements directly from the Choi operator. So instead of addressing the instrument directly, one can equivalently address the Choi states. So now we come to the problem at hand, which is projective instrument simulation. Given any quantum instrument, we ask whether one can simulate it using projective measurements. Specifically, we consider this kind of a setup. So we have a quantum state, and using a random variable lambda, we select a set of PVMs, and we select a set of quantum operations, and we ask whether we can simulate this instrument exactly. So we're given access to three resources. First of all, we have classical randomness. Second, we have projective measurements. And thirdly, we have quantum post-processing. So this is reflected in this mathematical equation, whether we can obtain the state omega A as first performing a measurement on the given quantum state, and then performing a quantum operation, and then mixing it up with classical randomness. And if this decomposition is feasible, we call the instrument projective or projective simulable. So the main result of our work is a theorem which gives a necessary condition for projective simulability. To present it.
Sorry, Shishir, can I ask something about the definition? So if I understand well, those you have some shared random, like some randomness lambda, and then okay, I want to understand it. Like you perform projective instrument e lambda, let's say, and then after getting the outcome, you're allowed also to perform some channel lambda, So my question is, like this channel, is it is it just a unitary transformation, or is it a general channel for you?
No, it's a general channel.
Okay, it's a general channel. Okay.
Actually, the theorem that I'll present, it does not hold when you restrict to just unitary channels. It's possible that it might give you a unitary as an optimal channel, but you cannot introduce this restriction in addition.
Right, and also just this channel can depend on the classical label A that you got.
Yes.
as well. Okay,
Yes.
makes
So
sense.
the label A is then it's transferred here as well. So that's how you select your quantum channel.
Okay, just
Depending.
one, because you know I'm like, as you know, I'm like invested in those problems. So just one more question, one more
Sure.
question. So can you do? Because I can imagine that you can maybe do some stochastic transformation. You know, it's about definition at the moment. So that you
Uh-huh.
could do some classical stochastic operation on this random variable A after you got the outcome. So
Mhm.
and this like outcome of the stochastic operation would then maybe transfer to the later stages. Does your formulas allow for something like this? Uh,
Um, well, because we have shared random, we have classical random variable with which we select the projective measurements and the channels. Aren't we
mhm.
doing that already? Or am I misunderstanding your
Well,
comment?
yeah, so I just in full, you know, it maybe doesn't matter, but like technically you could allow for some classical processing after getting the outcome A, right?
Uh-huh.
Uh,
A classical
uh,
post-processing in the sense of your paper as well.
yeah. And like this like outcome of this process and this processing can of course also depend on lambda perhaps, right?
Uh-huh.
And this processing you like outcome of this processing you could maybe feed forward to the second stage of your simulation, like to the
Mhm.
lambda and to the outcome. But okay, those are like
Yeah.
nitpicking things.
Uh-huh.
Just yeah.
We haven't really considered it, but I'm not sure if it'll be helpful because you also showed that it was not necessary in the end to consider classical post-processing in that scenario, right?
That is, it's true, but
Yeah.
it was a different setting a bit,
Hmm.
right?
Yeah.
And you
It's true.
could
Yes.
do, yeah, okay, those are like maybe, yeah, just
Yeah.
go ahead. Sorry, I just wanted to understand. So you basically have deterministic relation between the outcome that you got from
Yes.
the from performing the instrument, projective instrument, and the outcome, and deterministic relation between that outcome and the map you perform on the
Exactly.
later stage. Cool,
Yes.
cool.
Uh, so let me come to the theorem, which gives the necessary condition for projective simulability. For this, first we associate every n outcome PVM with a rank vector, such that the every element in this rank vector is just the rank of the corresponding projector. So you can see that the sum of these elements in this rank vector has to sum up to D, and every n tuple such that the sum of the elements is D is actually a valid rank vector. And with this association, we can now come to the theorem one. So for any n outcome projective instrument, if eta A are its Choi representation, there exists a decomposition of this kind, which is decomposing this Choi operator into other subnormalized Choi operators which satisfy certain trace conditions. And in addition, we also have a constraint on the Schmidt number of this Choi operator sigma A given R. And let me remind you that the Schmidt number is the minimum Schmidt rank over all possible pure state decompositions of a state. And it characterizes the dimensionality of entanglement. So what this theorem does is reduce the projective simulability of instruments to a kind of entanglement classification problem. You can also
Uh,
notice that all of this, sorry,
so can I ask? So
yes,
technically, you have an outcome projective simulable instrument, not projective instrument, I guess. So this is
yeah, it's
characterization of projective simulability.
exactly, but
Okay,
we in the paper we're calling projective simulable instruments projective instruments because
okay.
yeah, it's just a matter of just relabeling, I think.
Gotcha.
Yeah, and you will notice that all of these conditions are SDP compatible except for this one, for which there are some relaxations available. However, if we're dealing with qubits, we have a further simplification. We can replace this by positive partial transpose as well. So let me sketch the proof of this theorem. So first of all, we write the classical random variable this way, where now x is classical random variable and r is the chosen rank vector. So I can decompose, if I have projective simulability, I can decompose the application, the post-measurement state upon the application of the instrument this way. And I can note that this map S, which is basically the application of the projector on the state, and after that applying the quantum operation, is trace non-increasing. And with this, one can easily show the first condition on the trace on the decomposition of the state, where I've defined now the Choi operator corresponding to this map as sigma tilde, and I've taken this probability inside this sigma tilde and redefined sigma, something like this. So the other trace conditions on these Choi operators sigma AR, they naturally follow if you note that if you know this definition, where QR is now the overall probability of selecting a particular rank vector among all the available ones. So the trace conditions are quite easy to obtain. You can also note for the Schmidt number condition that if I locally project the maximally entangled state on any projector EA, it will confine it to an RA dimensional subspace. And if we now apply stochastically some local channels, say lambda A, they cannot increase its Schmidt number. And this will overall mean that the Schmidt number of these subnormalized Choi states is now restricted by the rank of the projective operators that you consider. It's also interesting to consider what happens when the instruments only deal with qubits. So for qubit instruments, it can be shown that the theorem, this is theorem 1, is necessary and sufficient. So for the proof, one first has to note that there are only two kinds of rank vectors for qubits. One is when you just have 2 in one of the elements, and the other is having 1, 1 in 2 of the elements. So here Si would be the rank vector with 2 in the ith position, and here Tjk would be the rank vector with the ones in the j and kth positions. And up to permutations, these are the only types of rank vectors you can have. And corresponding to these ranks, you can only have the identity matrix as the projector for Si. And for Tjk, you can have 2 orthogonal projectors, which are represented this way. And using this observation, one can show that the Choi state of the instrument can be decomposed in this manner. So on the one hand, this rank vector Si gives me some generic subnormalized Choi state. And on the other hand, Tjk gives me a generic trace half separable state with some subnormalization attached to it. And with this, we were able to prove that the decomposition in theorem 1 actually implies projective simulability for qubit instruments. Now, sorry, if there are any questions, I'm happy to.
So just to clarify, so your first theorem is a like sufficient condition for projective simulability?
It's a necessary condition. It's not a
sorry,
sufficient
necessary.
condition.
It's a necessary condition. Oh,
Exactly.
okay. And
So
you. Mm-hmm.
so QR here, as I said in the proof, is the probability of selecting a rank vector R.
Mm-hmm. Mm-hmm. So should I think about this rank vector as like basically applying projective measurement that has the type that like that ranks of its measurement operators are exactly like this tuple R. Is that?
Y- Yes, so a particular rank vector will basically give you the structure of the PVM,
I see. I
but
see. So
it will
you,
not determine the PVM exactly.
yeah, because you have like unitary freedom, for example. Okay. Mm-hmm. I wonder how just how this possibility, like whether your proof is still intact if you allow for this additional post-processing happening,
Mhm.
you know. But well, okay, it's yeah, it's more technical for let's maybe talk about it later. Cool.
Sure.
And so about qubit case, uh, do you get like some like algorithm that gives you a decomposition or like some as like yeah so you have as do you get like SDP at the end SDP program for projective
So
simulability?
yeah, so for qubits, we don't need any relaxation. In the end, we have an STP which is exact.
Mm-hmm.
Yeah.
Okay.
But for
Uh,
if we go to higher dimensions, and I'll give you an example later, we do have, well, it's already relaxed because it's only a necessary condition. We have to introduce a further relaxation because we have a Schmidt number constraint, which is not STP.
mm-hmm. Okay. Okay. Cool. Thanks.
So now I come to some applications, and the first application I consider an unsharp basis measurement of this kind. So this is an unsharp weak Z measurement where gamma is a sharpness parameter. You may notice that if you take gamma equals 0 or 1, you will obtain a strong Z measurement, which is actually projective. We would like to add some noise to this measurement and check at what level of noise does this instrument become projective simulable. So we've taken specifically three kinds of noises. First is dephasing noise, which is given by this expression. Second is white noise. And third, we allow for arbitrary noise and worst case. So the noise that makes the instrument least simulable. And we ask at what level of noise with these models is the instrument projective simulable. And for this, we can write an SDP. And you might notice that here, these conditions are exactly from theorem 1. So here we've taken the full instrument with the noise and set it equal to this decomposition of subnormalized Choi matrices. And I've replaced the Schmidt number condition now by positive partial transpose. And you can also convince yourself for the other type of rank vector, when I have 2 and 0, I actually don't have any constraint here because its Schmidt number is always constrained by 2 anyway. So with this, we were able to, so with the SDP, we get this kinds of curves. Here is the visibility along with the sharpness parameter. As I said, that the instrument is projective for gamma equals 0 and 1. So here we have visibility of 1. And we were able to derive in all three cases the analytical models that correspond to these curves and match them numerically with the SDP. We can notice that large levels of noise can be tolerated before the instrument becomes simulable. And the minimum visibility, which is around this point, is exactly at 1 over square root 2 for the worst case and dephasing noise. but it's slightly smaller for white noise. And you can also notice that the instruments become less and less simulable as we get closer to gamma equals 1, because the curves are getting sharper. So it's beyond these basis measurements, it's also interesting to consider extremal instruments corresponding to extremal measurements. So we also considered the SIC instrument plus white noise, and it gives the critical visibility of 0.773. And this is much smaller than when you consider the POVM only. So when you disregard the measurement, the post-measurement state. So it kind of highlights that in some situations it is useful to consider the full instrument because the full instrument happens to be significantly less simulable than the measurement only. So as the second application, I will consider an information disturbance problem. The information disturbance principle states that extracting information from a system inevitably introduces some back action. So in some situations, it's quite useful to consider the trade-off between this information disturbance, because in some situations you would like to extract as much information from a system without disturbing it. So with this motivation, we consider the block hemisphere discrimination problem. So consider that we randomly and uniformly draw pure qubit state, and we would like to determine whether this qubit state is in the northern or the southern hemisphere. So in this situation, we can perform some arbitrary quantum instrument with the outcomes north or south. And we're concerned with two things. We're concerned with the success probability, and we're concerned with the fidelity of the post-measurement, the average fidelity of the post-measurement state with the initial state of the system, which is psi. And we would like to maximize the fidelity. So we would like to maximize how well we preserve the state such that we obtain a minimum amount of information from the system. So we're setting a lower bound on the success probability. And as before, going to the Choi picture is quite useful here because the expressions for the success probability and fidelity take this very simple form. And now we can apply our STP method, write an STP and obtain these two curves. So for projective instruments, we find this linear curve. And for quantum instruments, we find something that goes beyond and is nonlinear. You will notice that the success probability is only going from 0.5 to 3 over 4. The case of success probability 1/2 is just when you do nothing to your system and you just flip a coin and say whether it's north or south. On the other hand, this 3 over 4 bound is the Hellstrom bound here. So we cannot obtain a success probability greater than this. So for both these cases, we were able to determine analytically the models that maximize this trade-off, that optimize this trade-off curve. For projective instruments, this is the form of Choi operators that we need, and this is the relation between the success probability and the fidelity. While for the full quantum instruments case, when you don't restrict to projective instruments only, the weak Z instrument happens to be optimal. And for this, and the weak Z instrument, as you can see on this block sphere, is represented by these Strauss operators Kn and Ks. And for this case, we find the upper bound on this, or rather the optimal trade-off for arbitrary quantum instruments, and it's given by this expression. So basically what we found here is that if we have non-projective instruments, then we will definitely have better than linear trade-off. On the other hand, if we have better than linear trade-off, we definitely have a non-projective instrument. So this is acting like a witness of non-projectivity. In general, our paper also gives a method to construct arbitrary witnesses of non-projectivities in quite general scenarios. Lastly, let me talk about briefly about the last application that we considered, which is the sequential Bell scenario. So in sequential Bell scenarios, we would like to use shared randomness between Alice and Bob to also violate a Bell inequality between Alice and Charlie, apart from violating between Alice and Bob. And this was first shown to be the case. So the possibility of this was shown in this work by Ralph Silva and others from 2015. So the goal here is to measure at Bob's side strongly enough to violate the first Bell inequality between A and B, but weakly enough such that you can also violate a Bell inequality between A and C. So naturally, unsharp measurements are quite natural to consider for these scenarios. But counterintuitively, you can also show that you can have projective measurements in classical randomness, and you can still have sequential Bell violations, which were shown first in this recent work. So specifically, we would like to determine whether we can use these methods and obtain better violations of better sequential violations of CHSH in such scenarios. So we consider the CHSH parameter between A and B, and the post-measurement state, which is channeled to which is related to Charlie, is given by this expression. Here, these KBY are just the Krauss operators corresponding to the instrument, the Wyeth instrument that Bob performs. And the CHSH parameter between A and C is given by this expression. Is AX and BY and CZ are observables for Alice, Bob, and Charlie. And a double violation, which we want, is obtained exactly when both these CHSH parameters are greater than 2. And using a convex, alternating convex search, we were able to determine this optimal trade-off curve, which is given in blue here. And for comparison, this point, the red point has been taken from reference 2. So what we find is that projectively we can obtain much larger violations of sequential CHSH violations than previously known using our theorem 1 and 2. So lastly, let me also talk about. Sorry, if there are any questions, I'm happy to answer. None in the chat. Okay.
So sorry, maybe one thing, like maybe I missed this. When projective simulable instruments where projective simulable instruments enter the game here, like when you do like you in this curve you optimize over projective simulable instruments, or you you have general instrument on the Bob side.
So here we only optimize over projective simulable instruments. So every point in the curve, we're only performing projective simulable instruments at Bob and at the 3 sites.
So do you expect that with general instruments you can go beyond, right?
Yes, maybe. For sure.
Okay.
So lastly, let me also give an example of a high dimensional instrument. And here I'm considering the generalized weak Z measurement that I showed you before, but in higher dimensions now. And you will notice that if I take qubits, so dimension d equals 2, I obtain again the weak Z measurement that I showed you before. You might also notice that the instrument is no longer projective when you take gamma equals 0 if you have dimension greater than or equal to 3. And as I said before, theorem 1 in higher dimensions is necessary, but not a sufficient condition. So the STP only gives us an upper bound. So here I'm showing the curves obtained with the SDP. The solid curves are the ones that I showed you before for d equals 2 for a qubit instrument. And the dashed curves correspond to a qubit. So as I said, the instrument is no longer projective for gamma equals 0. So we find that the visibility drops below 1 for all three cases. And we also find that the visibility drops quite significantly upon increasing dimension. So it motivated us to look at analytical solutions for the visibility beyond dimension 2. And we were able to do it for dephasing and worst case noise. And specifically with dephasing noise, we found that the upper bound that we obtained from the SDP is taking this form. And at large dimensions, this scales as 1 over square root of d, which as you can notice goes to 0 in the limit of infinite dimensions. This means that we have an unbounded advantage in non-projectivity when we consider large dimensions. But is this expected from all noise models, or is the dephasing noise is it quite specific? So with this, we considered the worst case noise model, and here I'm not presenting the exact expression for the worst case visibility. I'm rather expressing the bottom of the curve, which is the minimum of the visibility, and it takes this simple form. And at large d, this is low. This goes to exactly to 1/2. So this means that when you consider this particularly bad choice of noise, the instrument is at least 50% noise robust. So we don't have a scalable advantage in non-projectivity when we consider high dimensions. So
sorry, can I just wanted to understand. So
yes.
So you have like the phasing noise, then for you know that basically only starting very like small visibilities you can simulate with projective instruments, but in general you don't know, because let's say if you are mixing with something else, it might be that you have that it's always a constant still, right?
Yes, indeed. But with dephasing noise, we find that it does not approach a non-zero constant. While
no,
considering,
sure. Give me a second. Oh, okay. So there exists one. Okay. So what? Okay, I understand. So what is the second bound? It's like.
So
in what sense this is worst case, let's say?
It's worst case in the sense that you cannot have a noise which gives you a higher visibility. So if I go back to these curves, you can see that the worst case noise is on top. So it's giving you the most noise robustness in your instrument.
Okay, cool. And can you give some intuition what this instrument is doing? Like really, like so to maybe grasp your results like intuitively.
So I don't have physical intuition for the analytical model that we could derive, but it can be found in the paper. I can show it to you after the talk if you like on the screen.
Thanks.
But it's not something that's particularly intuitive. It's just something that comes out with from the SDP, and we were able to numerically match these expressions. So basically, what we found is that there can be dimension scalable advantage with some noise models, but not with all of them. We can have particularly bad noise models where we don't find this scalable advantage. So with this, I would like to conclude. So our work presents the first theory of projective quantum instruments. And we were able to completely characterize qubit instrument simulability. We also have a relaxation for higher dimensional instruments. Importantly, our methods are quite computationally tractable, STP compatible, and quite broadly applicable. I showed this with 3 examples. And we also found a scalable high dimensional advantage in non-projectivity for a certain noise model. So this I would like to thank you for your attention.
Thank you, Shashi, for a very nice talk. Yeah, we have now time for questions and comments to the speaker. So if anybody wants to ask something, just unmute yourself and okay. I maybe ask. I just maybe want to just touch on this last point, because yeah, like we had like some like related results on for the case of POVMs, not instruments. So I want to just understand it well, like because what you showed is when you mix with dephasing noise, the visibility would be pretty small. But let's say from the resource theory perspective, let's say if you don't view this as noise, but as, let's say, you have, say, some non-projective simulable instrument, and perhaps you want to mix it with something to be projective simulable, basically your results don't exclude the possibility that you're gonna just have a constant visibility when you mix with other types of noise, right?
By constant visibility, you mean?
I mean like not like just bounded advantage, let's say, because at least for POVMs, those like one can study, or for any resource theory, convex theory, resource theory for that matter, one can study like this generalized robustness, right? So the minimal, you have your resource like object, and you are interested about the minimal like 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 you mix it with something else, okay? And you want to know what is the like minimal amount of minimal probability mass of this thing with which you mix, such that you become free again, right?
Yes.
Like in your case, projective simulable. And so if I understand well, like your results like uh, don't prove that this generalized robustness is constant, like but just for specific model the like this visibility would be small, if I understand well, right?
Exactly, yes. Yes, that is true. So this unbounded advantage is only for specific noise models. Maybe there are other models that are
Gotcha.
physical
Mm-hmm.
where we find
Right.
the same thing, but this is not to be
Uh,
expected of all noise models.
right. Because just for us, in some earlier works with about projective simulability, we had some specific scenarios that yeah involved simulation with post-selection, and then we also had unbounded yeah like something analogous to your visibility was decaying with dimension, okay? But that was just some specific, yeah, some specific noise model again. Okay, uh, cool. All right, so maybe there are some other questions or comments to Sashir. Personally, I would be like very much interested to understand whether this SDP criterion that you show like captures automatically this possible post-processing that you can get. I mean, it's all legit. I'm not criticizing it, but just logically, you have a possibility to to do this classical processing after you got classical outcome.
Mhm.
Somehow both to get the outcome and additionally you can also do maybe some other processing, classical processing before applying the map.
I understand.
Right?
Mhm.
Yeah, but I wonder. Yeah, still very very nice results.
Thank you.
Mm, okay. Um, okay, so last chance to ask something. Okay, sorry for taking the floor so much because it's like related to some of the stuff I was doing recently. Maybe like just last chance to ask something to Shishir. If not, we conclude for today. I don't see any questions. So then, okay, let's thank the speaker again. Thank you, Shishir. Thanks, Armin, for dropping by.